Hello, my name's Bethan. I'm a PhD student at the University of Bristol, and this lecture is going to be a little insight into what it's like to be a PhD student, why I decided to do chemistry, and a little bit about what my research is actually to do with. And so we'll get onto the photochemistry for drug discovery a little bit later. Um, I'd start by just kind of showing you how I got to being a researcher in chemistry. So I grew up in a town just north of London called Harpenden, and I spent all my school years here, did my GCSEs here, and then picked my A levels. And when I was doing them, we picked four A levels. So the subjects I chose were chemistry. That was my favourite subject at school. I really enjoyed doing it. And alongside that, I wanted to do some kind of similar sciencey subjects. So maths was another one I chose, along with physics. And as well as those, I wanted to do something a little bit different. I didn't want to kind of do all sciencey subjects, so I also picked to do textiles, which is something I really enjoy. I still enjoy doing textiles, and I have quite a creative side, so it was nice to have that side to my studies as well. And I'll talk a little bit more about that in a minute. But when I finished my A levels, I decided to go to university. I was still really enjoying chemistry, so that was the subject I decided to study. And I moved to Bristol in 2012 to start a master's degree there. I looked around quite a few different universities. Bristol was the one that kind of caught my eye. The teaching labs there were great. All the facilities for doing chemistry were fantastic. And the city itself is really beautiful, and I really enjoyed living there. So um, I was there for 4 years. I did a master's degree, and then when I finished that, I wanted to decide what I wanted to do, and obviously went on to do a PhD. So I'll talk about a little bit more about that. So why did I choose to do chemistry? Well, like I said, it was one of my favourite subjects at school. I really enjoyed all the practical side of it and making things and doing things kind of with my hands and actually getting hands on with the science and with the chemistry. Um, so, and I kind of think my creative side also comes into this. So, as I said, I'm quite creative. I like making things, I like doing things with my hands. And chemistry is kind of a way of combining those two things of science and a little bit of creativity. And you'll kind of see that a little bit later on, the kind of creative side, how that impacts on my research that I do at the moment. So, I quite like this quote: chemistry is like cooking, just don't lick the spoon. So, as I said, I'm a PhD student, but what does that actually mean? Well, obviously, you guys that are listening to this probably are at school at the moment, maybe doing GCSEs, maybe doing A levels, but you'll be coming to some sort of decision as to what you want to do next. And for some of you, that might mean you want to go to university and study further, and that's exactly what I did. And a lot of courses have different options. So, you can do a bachelor's degree, which is usually 3 years, or you can then go on and do a master's degree, which is a further 1 or 2 years on top of that. But what I decided to do is what's called an integrated master's, where you kind of decide to do both of those all at once, and it's all sandwiched together into a 4 year course. So I finished my master's degree in chemistry, and as part of that, for my final year, I got to do a research project in a lab, and I really enjoyed this. And this is kind of where you work in a research lab on brand new science, which was really exciting. And it was kind of a little taste as to what a PhD would be like, which is what I'm doing now. So I just liked it so much that I decided to stay, and I decided to stay in Bristol as well. So I'm currently at this stage where I'm doing a PhD, and this is usually about 3 or 4 years. It's all done in a research lab, so you have your own project that you work on. You work alongside other students, other PhD students that are working on the same sort of area. And then at the end of the 3 or 4 years that you spend in the lab doing lots of different experiments, you write it all up into a big thesis. It's usually kind of a couple of 100 pages long. You write up all your results, and then you have a viva at the end of it, where you basically will get asked questions, usually for a couple of hours, on the subject that you've written up. So I've got about a year left of my PhD, maybe just less now, and I'm starting to think about what I would like to do next. So one of the things you can do if you wanted to stay in the research environment, and something that I'm thinking about doing, is staying on as a postdoctoral researcher. So these are researchers that work in a university that already have a PhD, and usually these last for about 1 or 2 years, but you can go and do quite a few of these different placements in different universities. So that sounds quite appealing to me. And if you end up wanting to stay in a university in an academic environment as a researcher, you can work your way up and eventually become a professor. So that's kind of how you get along in an academic kind of career. What do we actually do as research scientists? Well, I'd say a lot of my day revolves around reading, writing, and analysing data. So this is some of my data that I've got here. We spend a lot of day kind of planning the experiments that we're doing as well. So this is my lab book. We have to write down all our observations for reactions, and then also kind of plan how we're going to carry those reactions out. I spend a lot of my day actually in the lab doing experiments. So this is me in my fume cupboard, setting something up. We also do a lot of teaching and marking. So as PhD students, we're expected to do some teaching of undergraduate students. So this is us in our rather lovely orange lab coats in the teaching labs in Bristol. And alongside that, we also kind of sometimes do workshops and do marking of students' work as well. And a very important part of my day is also drinking a lot of coffee to keep me going. So as I said, I work in a research group and we all have kind of a similar research interest. So I'll talk a little bit about what our group is interested in. So we're interested in two different areas of chemistry. One of them is the chemistry of palladium. Palladium is a transition metal element. And the other area of chemistry that we're really interested in is photochemistry. So this is using light to do chemical transformations. And they seem like two fairly disconnected ideas, but actually they both allow us to make really complex molecules. So palladium is a really good catalyst. It can be used to catalyze reactions that wouldn't normally happen. And photochemistry or light can also kind of act as a method for making these really complex molecules. And I'll talk more about photochemistry because that's the side that my work is on in our group. So these are some examples of some complex molecules that we've made using these two different methods. And just as a little reminder, the skeletal structure is shown at the bottom there. And as chemists, we tend to use these skeletal structure for these more complicated molecules. You can see the displayed structure shown above, where it's got all of the different hydrogens all drawn out, but actually we just ignore those and just draw the bonds between each of the atoms instead. So hopefully you're comfortable and familiar with that, but I'll be using those skeletal structures throughout the presentation from now on. So why do we need complex molecules? Why do we need these methods to be able to synthesize them? Well, hopefully you might recognize some of these molecules. So usually I get people to guess, but so have a think, see if you can see what this one is. So this one is paracetamol. We have another common drug molecule here, and this one is ibuprofen. And a final complex molecule that's also used as a drug here, this one is the antibiotic penicillin. So you can see that actually drugs are all complex molecules. They're all molecules that need to be synthesized. But we have these molecules already. We can buy them in shops. They're already very readily available and they work for a number of different things. So why do we need to be able to synthesize more or synthesize new ones? The reason for that is antimicrobial resistance, or AMR, which I'm sure you've all heard of. It's in the news very commonly. And what this graphic is showing is that by the year 2050, antimicrobial resistance is actually predicted to overtake cancer as one of the leading causes of death globally. So this is a really big issue and it's something that we need to address. And we can address that by starting to think about ways of making new drugs or drugs that work in different ways so that the bacteria that we're using them against won't be resistant. And there's lots of different ways we can do this, and there's many different scientists working on this problem, not just chemists, but biologists as well. So let's have a think about how drugs are actually made and the process of drug development. So pharmaceutical companies, big pharma that put a lot of money and time into synthesizing or coming up with these new drug compounds will often start with a big library of compounds that they think might be potential drugs. And so this can often be about 10,000 compounds, and these all might be very similar in their chemical structure. But what they will probably have is different, very small changes in their functional groups. And what the chemists and medicinal chemists will do is they will screen a large number of these compounds against a different target. And they'll look for any potential activity or bioactivity within these compounds. And what they can then do is look at all the drugs that were successful and pick out which functional groups in those molecules were responsible for the good activity that they observe. And that can help to narrow down the potential compounds that will be successful until they get to kind of a smaller number that can be tested. And this is when a small number of compounds may go through clinical trials. So there's different phases here where they have to test the effect on the body, how safe the drug is, whether it's actually effective in treating the disease, and then also some kind of longer term safety issues. So overall, this process takes a very long time, and it can often be 10 to 15 years before a drug is actually available. And also, a lot of money goes into this process. So it's going to often cost about £2 billion just to develop one drug. So that's all great, but how are those 10,000 compounds actually identified to start with? Well, if we think about just making every possible molecule that could be a good drug, actually, the number of combinations in which you can stick different atoms together to form a compound that looks feasible is actually a lot. And if, well, 10 to the power of 40, which I can't even imagine how big that is. But if you were to take 10,000 chemists and they were all to prepare one compound per second, it would take many years to finish the job. And so we can't just make every possible combination and test them all. We have to be a little bit clever about how we think about drug synthesis and how we target different drugs. So one method that we've used that has been very successful in the past is simply serendipity. So hopefully you're all familiar with the example of penicillin. This was isolated from a colony of penicillin. And it was noted that around this colony there was an inhibition of bacterial growth. So there was an area around which there could be no bacteria growing. And the compound that was responsible for this was isolated and found to be penicillin. And we now use this as a common antibacterial today. But just stumbling upon amazing antibiotic doesn't happen every day. We have to, again, try and be a little bit clever about how we think about creating new drugs. And another method for this is using inspiration from nature. So another common kind of case study for this is aspirin, which is a derivative of a compound that's isolated from willow bark. And again, it's a very useful antibiotic. It's used a lot, and it's used. Its effectiveness is due to it being derived from nature. So nature's got the advantage of having hundreds of thousands of years of evolution. So we can take advantage of that and isolate compounds that nature has already developed itself that we can then use for different things. A final method that's used to identify new drug compounds and that's being used much more commonly these days is computational chemistry. So using computers to simulate different targets. So here we've got a computer simulation of an enzyme, and hopefully you're all familiar with the enzyme kind of lock and key mechanism. So here the lock is the big enzyme that we're trying to target to have some kind of biological action, and the key is actually a small molecule. So if we can model what that shape and structure of that enzyme is, we can then design a small molecule, a small chemical molecule that we can fit into that lock very specifically, and that will hopefully then have the effect that we are after. So that prevents us from having to make a lot of chemicals, a lot of molecules in the lab. We can just design something that is much more likely to be effective. So I'm going to start talking a little bit more about my research, and this fits into the kind of using inspiration from nature method for drug synthesis. So my research is all to do with this molecule called vibraspiran. And this research was published by a biological group who took this plant and isolated some compounds from a fungus that grew on it. So they do that by growing up lots of cells of this fungus, and then they do various different extraction techniques. I'm not a biologist, so I'm not going to talk too much about this. But one of the methods they use is chromatography, and they use this to separate out lots of different compounds in a mixture. So here, you might be familiar with thin layer chromatography, or TLC, which you do kind of on a flat plate. But we can use this method kind of more on a larger scale in a cylinder of silica. So this is the same solid phase that you would get on a thin layer chromatogram, but we use it in 3 dimensions to put a large quantity of a substance onto that and separate it out to isolate the compounds that we're after. And when this research was done by the biological group, one of the molecules that they isolated was this one, this called vibraspiran. And the reason they were interested in this compound specifically was because it was found to have potential antifungal properties. So my research is to take this compound and work out how we can synthesize it in the lab. So when this compound is isolated from nature, it's actually only isolated in very small quantities. So if we want to use this as an antifungal, we have to be able to synthesize it in much larger quantities. So let's have a look at the chemical structure of this compound and see if we can pick out some of the different functional groups. So hopefully you can all recognize this alkane chain here. It's got two different ring systems. So one of them is 8 carbons all in a ring, so that's the octagon one, and then also 6 carbons that kind of forms a bridge across the other one. That's the other ring there. And then we've got a methyl group, so it's just a CH3. We've got an alcohol, and we've got these 2 anhydrides, which I'll talk a little bit more about in a minute. So this is what the representation of the molecule looks like when we draw it out flat. But actually, molecules aren't flat, they're three-dimensional. So this is a three-dimensional model of fiberspiran. So you can see it being rotated now. We've got the long alkane chain, which you can see hanging off the edge here, which kind of looks like a zigzag shape when it's in 3 dimensions. We've got the methyl group that's shown there. And then if we rotate the structure around a little bit, we can see the alcohol poking off one side, that's there. And then if we rotate this again further, it's a bit clearer to see those ring systems. So we've got one of the larger ring, the 8 carbons all in a circle there. And then we've got that bridge that forms a 6 carbon ring that's at the top there. Finally, we've got these 2 anhydrides. So these are at the top there with the oxygens shown in red. So there's one at the top and there's another one at the bottom there. So these are probably new functional groups that you might not have seen before. So I'll talk a little bit about how these are formed and what these anhydrides. So that's a little bit of background on the molecule I'm trying to make, but I talked about earlier about our group being interested in photochemistry, and actually that's one of the methods that I'm going to try and implement into this synthesis. So photochemistry, like I said, is the use of light to do different chemical transformations. And when a certain wavelength of light interacts with an atom, it's the electrons in that molecule that can absorb that energy. So the electrons will absorb the energy, and what that will allow them to do is jump up to a higher energy shell or subshell than they would normally occupy. And we call this an excited state. So when we've got an electron in a higher energy level than it should be, that's an excited molecule or an excited atom. And that electron can emit some energy and drop back down to where it was originally in its ground state. Or in photochemistry, what we tend to do is take advantage of this excited state. So excited state molecules are really good at doing interesting transformations, and we can give them things to react with that will allow them to do those transformations. So if we look at the spectrum of radiation, it's usually the kind of ultraviolet or visible regions of this spectrum that we use to excite electrons in lots of atoms and molecules. And we use UV visible spectroscopy to work out what wavelength of light we need to use. So we can, for example, for isoprene, we can run a UV vis spectrum, and that will tell us which wavelengths of light are being absorbed by that molecule. And therefore, we know that that's the wavelength of light we need to shine in order to get the molecule to absorb that energy and become excited. So that was the theory of photochemistry, but how am I actually going to implement that into my synthesis? Well, the reaction that I'm looking at using is what's called a 2+2 photocycloaddition. So this is a reaction of 2 alkenes. So that's where the 2+2 comes in. So we've got 2 atoms on the left and 2 atoms on the right. And normally if we were to mix these alkenes together, maybe heat them up a bit, there would actually be no reaction. Alkenes are not reactive with each other. However, if we know what wavelength of light will cause those alkenes to become excited, then actually they do start to react with each other. And they form what's called a 4-membered ring or 4-carbon ring, where those electrons in the double bonds combine to form 4 carbons that are all joined in kind of a square. And these rings have what we call strain energy. So normally in a normal kind of tetrahedral carbon, those bond angles want to be 109.5 degrees apart from each other in order to separate those electrons in the bonds as far as possible. But in these 4-carbon rings, we're forcing those bond angles to be 90 degrees, which makes these molecules strained or have a lot of energy. They don't want to be like that, and they want to react further. And that's what I'm going to take advantage of to make those bigger rings that are in my molecule. So what you can do is take a cyclic alkene, like this one, cyclohexene, and react that with another alkene of some sort. And what you get is these two fused rings where we have a cyclohexane and a cyclobutane both joined together. And because that ring in the cyclobutane, the 4-carbon ring, is very strained, it wants to open. And what that means is the bond that fuses the two rings together can break and do what's called a ring opening reaction, where we actually end up with an 8-carbon ring. So have a little look, see if you can work out how that reaction is happening. But what that means is I can use this type of chemistry to build up the core structure of my molecule. And actually, the reactions that I'll be using are much more complicated than the simple ones I've shown here, because there's lots of other functional groups that I have to consider. But this is the kind of basic outline of what I'm trying to do to create this structure. So how do I actually carry out photochemical reactions in the lab? Well, we've got two different ways of doing it, two different reactors that we use. One of them is called a batch reactor, and the other one is a flow reactor. So in batch reactors, you put all of your reagents into the vessel, you stir it. In our case for photochemistry, we'll shine the wavelength of light that we want to use at it. And then at the end, when the reaction is complete, you take all that out and you get a fixed quantity of your product. In a flow reactor, instead of having everything all in at once, we actually constantly flow our starting materials in and we constantly take our products out. So this allows you to carry on the reaction for as long as you want. You can essentially make this infinite. You can carry it on and get whatever quantity of product you want out. So there's a big advantage to using flow reactors for photochemistry. We do use batch reactors sometimes, mainly for when we're trying things out or testing things for the first time. So these are a few photos of our batch reactors that we use in the lab. So you can see the UV light that we use that's kind of suspended in the middle of the reaction. You can hopefully see the level of the liquid, so that'll be our solvent that we carry out the reaction in. And then what we also do is wrap these in foil, and that just helps reflect all the light back in. Along with this, we have to cool the lamps down quite a lot. So the lamps that you see there are actually surrounded by a constant flow of cold water, and that helps keep them cold. If we didn't do this, the lamps get up to about 800 degrees centigrade. So we definitely want to cool that all down so that we're not frying our reagents. The flow reactors look really similar, so we just constantly flow our material through a very thin tube that wraps all the way around the lamps. So in this case, you can see there's 3 lamps around in a line, and we can pass that those reagents all the way around and down one and up another and then back down again. And like I said, that allows us to produce a large quantity of material, and we can make up to about 8 kilograms per hour using this method. So that's pretty much all I'm going to say about my project. I hope you've kind of learned something. I hope it was interesting for you. So yeah, thank you very much for listening. And yeah, good luck with your further studies. Thanks.